Hello, everyone. Let us continue with the class now. Continuing with the error coefficient problems. Uh, Let us do this now. In this, find the step, comma, there is a comma, ramp and parabolic error coefficient for unity feedback system which have the following transfer function. Here, uh, what they are asking here is the step, ramp and parabolic. Here it is equivalent to, step means it is positional error coefficient or positional error constant. Ramp here refers to velocity error coefficient or velocity error constant, and parabolic will be acceleration error coefficient or the acceleration error constant. So it is the alternate name for those, that is for the uh, positional, velocity and acceleration would be step, ramp and parabolic respectively error coefficient. So similar to how we did the previous problems, we have 4 equations for which we'll have to find those 3 error coefficient. Considering the first one here, this value is nothing but g of s value. This is not, these values are the g of s values, and anyway h of s they have told it is the unity feedback system. So h of s will be equal to 1. In that case, what will we have? G of s into h of s. This is g of s. See, this is nothing but g of s. All these values are these are equal to g of s. So h of s is anyway 1. So g of s into h of s is nothing but uh, these values, these expressions itself. So considering the first one now, considering the first one here, the first, that is a positional error coefficient or the step error coefficient, that is one and the same, will be g of s into h of s. Here h of s is 1. So it is actually, it is g of s into h of s, but here because h of s is equal to 1, I have just written it as g of s. Okay, so that value will be, this is 1, so then this becomes limit s tends to 0, 50 divided by 1 plus 0.1 s into 1 plus 2 s. Substitute here, these values become 0. These are the values which will go to 0. This is 0 and this is also 0, so you're left with 50. Okay, next, coming to the next one, velocity error coefficient or the ramp error coefficient. That is nothing but s into g of s as limit s tends to 0. So s into 50 divided by the denominator. Anyway, when all these values go to 0, that is here we have these values going to 0. This is 0. This is 0. So this is also 0. So anyway, this expression will be equal to 0. Next would be the acceleration error coefficient or constant, or the parabolic error coefficient or constant. Here it is the same. Then it is ka is s square into g of s as limit into h of s. Okay, here also we have, here also it is s into g of s into h of s. Because h of s is 0, we have just written it as s into g of s. Please be careful, it is not only s into g of s, it is s into g of s into h of s. Because h of s is 1 here, because this value is 1, this value is 1, so I have taken this value as, I have not considered this value, so it is just s into g of s. Okay, I have not written this value here, I have not shown h of s. Here also it is same thing, here also it becomes, here it is going to be what, s square into, it is s square into g of s into h of s. Again, what is this? Here again this value is going to be 1. H of s is going to be 1. So it is s square into g of s. Again, here when you're putting s values to 0, which values will go to 0? This is going to 0, this is also 0, this is also 0. So the entire value will be equal to 0. Similarly, the second one. Now, second expression. In the second expression, we have to find positional error or the step error coefficient or constant. Again, it is g of s into h of s. H of s being 1, we have written it as limit s tending to 0, g of s. So here again it is nothing but what? What do we have? It is g of s into h of s. H of s is equal to 1. So it is only g of s which has been written here. Everywhere, because h of s in this case, in this entire problem, h of s is equal to 1. So I have not explicitly written it in the expression. But the actual expression will be limit as s tends to 0, s g of s into h of s, or s into g of s into h of s, or s square into g of s into h of s. But in this problem, because h of s, that is the feedback is 1, this h of s is not written because it is anyway 1. Okay, so now again putting all s equal to 1, where do we have s? That is, this becomes 0, this is also 0, this becomes 0, and this is 0. So here it is 30 divided by 2, so it becomes 15. The next problem, what is there? Here again it is s into g of s into h of s. H of s being 1, so it is s into g of s. Then which are the terms which go to 0? This is going to 0. Here we have this term going to 0. This is 0. This, and this. So because anyway here we have a 0 term, this expression will be equal to 0. See, this is equal to 0. 0 into whatever it is 0. Next, acceleration error constant or coefficient, or also known as parabolic error coefficient, because these values are for parabolic input. Then it is s square into g of s into h of s. H of s 1, so it is s square into g of s. Everything, because here anyway this is 0, so here this value ka will be equal to 0. Similarly, please try to do this for the third and the fourth expression. This is the third expression, and this will be the fourth expression. Here fourth expression, you please try to do it for the fourth expression as well. You get it in terms of the k value. Okay, so please do it. Next, and look at the order of the system here. What will be the order of the system? The first system, what is the order of the first system? It is, sorry, type of the first system is 0, because you don't have any pole at the origin. What about the second one? Do we have anything? No. Here also there is no, only s term is not present, so there is no pole at the origin. What about the, therefore we have, see, only the first positional error coefficient is there, because type is 0. Again, what about the third one? Here it is type 2. So for type 2, you will not have the first two errors. These two values will not be there. Only the third one, the acceleration error coefficient will be there. This is type 1. It is S. You have only one pole at the origin. For type 1, only the second value will be there. Only the velocity error coefficient will be there. The other two is not present. Okay, so depending on the type, you will have the different, you will get the error coefficients. Next, continuing with this problem, the next problem, for the transfer function given, g of s equal to 20 s plus 2 divided by s into s plus 3 into s plus 4. Find the static error constant. Static error constant here, they refer to the positional velocity and acceleration. Find the steady state error for the given input. Okay, r of t. Here again, as I was telling you, r of t means it is just, see, if you have seen, if you see here, how do we write, how do we write the here, how do we write the values, or block diagram? It is, then we have the block, okay, and again we have the output from this block. This block is going to be g of s, isn't it? What is the input for this block? What is the input that comes to this block? This block is nothing but, we write it as r of s, and here output will be c of s. So now what is this? R of s is a input. This is a input reference. R is the reference input. This is the output, controlled output, reference input. So it is in S domain, it is R of s. In T domain, it becomes R of, it is R of T. So this value, this is what it is shown here as R of T. It doesn't mean it is a ramp input. It is just an input, reference input. Okay. Then R of T, for this value of R of T, we'll have to find the error. Positional error. Here, first one, then they've asked us to find the error constant. So positional error constant Kp is limit as s tends to 0, g of s into h of s. Why haven't we written it as h of s? Here, why haven't we shown it as a, again here, this value, again, if we write here, if they have not mentioned, you can take it as unity feedback. Okay, if not mentioned, we can take h of s equal to 1. So it is not mentioned here, so we take h of s equal to 1. In that case, what do we have? It is only g of s. So that is what we have written here. It is limit s tends to 0, g of s. Please, in the book, make sure you write h of s. In the next step, if you want, you can write Kp is limit s tends to 0, g of s value, because h of s is 1. Sorry. Then substitute test equal to 0 here. What do we have here? Because anyway, denominator will have a 0. So this is going to be infinity. What is the type of the system? Type 1. See, you have one pole at the origin. We have one pole at the origin, so it is type 1. For type 1, we have velocity error coefficient, but the other two will not be there. So now next, coming to the next one, see, again here also it is s into g of s into h of s. H of s being 1, it is only s into g of s. S cancels. Again, substitute here. All these values will go to 0. This is 0. This value is also 0. And this value is also 0. In that case, see, this is 0. This is 0. This is 0. You have 40 into 12. Okay, 40 divided by 12, we will have 10 by 3. Next, what do we have? The acceleration error constant, or also it is known as the parabolic error constant or coefficients. It is limit as s tends to 0, s square into g of s into h of s. H of s being 1. Okay, h of s here is 1. So it is s square into g of s. Then 1 is cancels with the denominator, but you have 1 remaining here. So anyway, anything into 0 is going to be 0. So now for the given input, for the reference input r of t, the first term is a step of magnitude 3. The second one is a ramp function. Okay, so Laplace of that will be 3 by s. This is going to be 5 by s square. Next, do the first term. What is the what is the error due to the positional error? If you remember, what is ESS equal to? It is a magnitude, whatever the step function magnitude, whatever magnitude it has, divided by 1 plus Kp. Okay, what was Kp value? If you see, it was infinity. Substitute, it is 3 divided by 1 plus infinity. Okay, infinity. So it is nothing but 1 by infinity is 0. So second term here represents a ramp input. Ramp input magnitude is 5. What is E of S for a ramp input? It is going to be A, magnitude of the ramp, divided by kV. What is the magnitude of the ramp? It is 5 divided by, if you see, it is 10 by 3. So that is equal to 15 divided by 10, or it is 1.5. This is the, so total value. What is the total value? It is total E of E will be here. What do we have? 0 plus this term. This we'll have to add these two. This we'll have to add this as well as add this. So it is 0 plus 1.5. Error will be 1.5 due to the input. Okay. So these are the problems referring to the steady state error. Now coming to the second order system. Let us see the second order system and related problems to that. We have already finished the derivation part. The video was already uploaded. That is second order system and the roots, how to find the roots, and depending on the roots, how the system is classified as undamped, underdamped, overdamped, and critically damped. That generally the second order means S square. Okay, S square means two poles. System which has two poles are called second order system. General transfer function, if it is a RLC circuit, the transfer function of that RLC circuit will be 1 by S square LC plus SRC plus 1. If it is a mechanical system, it is going to be B. Okay, mechanical MSD here is mass spring damper system. Second order mechanical system will be B by S square plus AS plus B. Okay, here these values, that is here you have, if you remember, it is M square plus BS plus K. If you recollect from what we did in the first chapter, that is mechanical system, it is, if you remember how to write, it is M square. Okay, here it is usually 1 divided by M S square S to the power square plus B S plus K, if you remember. So that you divide, you take out M outside. Okay, in that case it becomes 1 by M divided by whole of S power S to the power 2 plus B by M S plus K by M. Okay, I am not able to write it properly. So you divide this value by this expression by M. We only want S square. So when you divide, you get this. Here B represents 1 by M, A represents B by M, and B again represents here 1 by M. K is the constant value here, sorry, spring value. Okay, so based on this, we get the general form of us for a mechanical system, second order mechanical system. Okay, now the general block diagram for a second order system is this one with unity feedback. Omega n square divided by S into S plus 2 zeta omega n. And the transfer function, this will be the transfer function. When you write, when you take G of S divided by 1 plus G of S into H of S, you get this expression, where omega n is the natural frequency and zeta is the damping ratio. These terms we have already defined what they are, but still again I'll tell you. Zeta is the dimensional, it is a quantity, and it depends, zeta means damping, means how the system will settle down depends upon the damping ratio. It is the ratio of actual damping to critical damping in a system or in a circuit. This was already defined. These was explained in the video. If you have doubt, please refer back to that. And omega n is the natural frequency or the resonating frequency. Omega d is the angular frequency at which the system will oscillate when there is a damping factor or damping ratio. Without damping, it will continuously oscillate. And if there is a damping, it is like a friction. It will take out some energy. That is, if you have, it keeps oscillating means partially the energy will get absorbed and finally the system will settle down. So that is damping. So the expression omega d is equal to omega n root of 1 minus zeta whole square. And based on the response, depending on the damping ratio, we have different response. Again, here also the root comes into picture. All this was already discussed. Again, this is just an overview before I start the problem. When zeta is greater than 1, it is called overdamped. Zeta equal to 1, it is called critically damped. And zeta is less than, okay, it is greater than 0 but less than 1, it is called underdamped. And when zeta is equal to 0, it is called undamped. Means there is no damping at all and the system will continuously oscillate. Okay. And in the overdamped system, here if you see, we have the waveform. Here I've written the waveform. See, this is C of t. Okay, this is C of t, and this is t, time. And for a zeta value, that is if zeta is 0, the system will continuously oscillate. It is this one. Okay, the system is continuously oscillating. Here this sine wave, if you see, that is for an undamped system. And if it is here, this value is the continuously oscillating system. And for this one, if you see, overdamped means what is the condition for overdamped here? Overdamped, if you see here, when will it be overdamped? When zeta is greater than 1, means it has more damping factor. The system will, without oscillating, it will try to reach its final value. It has more damping. More damping means it will not allow the system to oscillate. Quickly it will try to settle down. So where is that? Here if you see, where is that? It is overdamped, means this is overdamped. Okay, here this is the overdamped. Here this waveform, this waveform is the overdamped. Here see, this one is the overdamped. It won't allow it to oscillate. The damping factor is more, it won't allow the system to oscillate. Next, underdamped, it is less than 1. It will oscillate, but finally it will settle down. Critically damped here is when your damping factor here is 1. See, critically damped means damping factor or damping ratio is 1. It is critically damped. Critically damped means it is not like your overdamped. It will take some time, but finally the system will settle down. This will be the ideal condition, critically damped system. Okay. See, next, based on this, okay, this is for a second order underdamped system. For an underdamped system, we had derived the expression, output expression for a unit step function. For a unit step function, this was the output. C of t was 1 minus e power minus zeta omega nt divided by root of 1 minus zeta square into sine omega t plus theta. And what is omega? This is omega d, and this is the value of theta. This derivation was done in the one of the videos. You can please refer back to this. This is the output C of t expression for an output of a system with step input, and it is underdamped. It is in the underdamped condition. And this is the response for an underdamped waveform for an underdamped system. Okay, here zeta is less than 1. It is greater than 0 but less than 1. The system will oscillate but it will settle down. It is not like overdamped, where it will overdamped means it will be like this. Your overdamped is something like this. Overdamped will be like this. Critically damped, it will be like this. Okay, it will be like this. It is neither in these two. There is a damping, so there is a small amount of damping, so it will oscillate and settle down. So based on that, this is the final value. This is 1. Okay, 50% of this 0.5. This is 0.5. So 50% of this is 0.5. So then 50% of this is settling time. Then this is the raise time. Raise time is when you're reaching the 90%, or if it is a underdamped 100% value, that is called a raise time when it reaches the 100% value. Then this value here, this value is called the peak time. Sorry, yeah, this is the peak time. That is the time taken for the system to reach the first peak. And this is the peak magnitude, MP. What is the maximum overshoot? First overshoot value is the maximum overshoot. And this is the settling time. Till it reaches the output with the tolerance of 5 to 2 to 5% allowable tolerance. Okay, so for these for these we had already derived in one of the videos. We have derived the TR, TP, and the maximum overshoot values. TR value is here, pi minus theta divided by omega d. TP will be pi by omega d. Substitute for omega d. MP is E, that is the overshoot value. Percentage overshoot means you'll have to multiply it with 100. Okay, and here if the system is subjected to step input of A magnitude, then the peak response is going to be A into this value. The peak responses, you'll have to multiply this term by A. The output at infinity or at a steady state, it is going to be anyway. Here we have taken it as 1. Instead, if it is going to be A, output, the magnitude, instead if it is going to be A, so at infinite time the output is going to be A. So now considering that at infinity it is A. So what is the peak overshoot? Max, that is overshoot. How much? What is this value? This overshoot value from here to here, it is A minus this value. It is this, the maximum value, difference between this and this time. So that is going to be, that is here, difference between these 2 points is the peak overshoot. This is at infinity and this is the magnitude when there is a first overshoot. So that is going to be, it is C at TP. TP is what? When you have the time, this is TP, this point at TP you will have the maximum overshoot. So substitute C at TP. Output at this time is this value, the maximum peak value, minus C infinity, the steady state value. You will get this output, A into E minus zeta divided by pi into root of 1 minus zeta square. And settling time for, this is the settling time for 5% tolerance and this will be for 2% tolerance. Now based on this, we will start with the problems. Okay, response of a servo mechanism is C of t 1 plus 0.2 e power minus 60t minus 1.2 e power minus 10t when subjected to unit step input. Obtain an expression for closed loop transfer function. Obtain the undamped natural frequency. Which is the undamped natural frequency here? It is omega n and damping ratio zeta. The output C of t is this expression. Take the Laplace of this. Okay, e power minus 60t is s plus 60. This is s plus 10. So then you take out the common and finally you get this expression. When you take out the common factor and reduce it, you get 600 into s square plus 70s plus 600. And the input, they have mentioned the input as step input. Okay, you separate this you have s, you can write it as 1 by s into this remaining term. You can write this as one term and this will be another term. So now when we split this and write, you can write it as 1 by s into 600 into s square plus 70s plus 600. So this 1 by s is nothing but our step input, unit step input. So that is represented, this is represented as rs. Then the remaining term. Then transfer function, what will be the transfer function? What is the transfer function then? It is C of S by R of S. This part will be the transfer function. This is going to be the transfer function for us. This will be the transfer function. That is what we have represented it here. Now, comparing these two, if you remember, this was a transfer function for a second order system. Okay. So now what is omega n? It is omega n square is 600. So omega n is root of 600. Then see, omega n square is 600. Omega n is root of 600. That will be around 24.49 or 24.5. Then here this 2 zeta omega n is nothing but here. Okay, I have forgotten to write one term here. There should S is there. Okay, I missed S, writing S along with this term. There should be a S value here. Okay, along with this term there is a S. See this term, this S I had missed. It is 2 zeta omega n into S. So now comparing these two, this S is nothing but here this 70 will be equal to this term. So then what it is, 2 zeta omega n is 70. Anyway, we know omega n value, find out the zeta value. So this is the problem, first problem. Now coming to the second one. This is the second problem here that we have. The second problem. Okay. Unit feedback system is characterized by an open loop transfer function g of s equal to k divided by s into s plus 10. Determine the gain k so that the system will have a damping ratio of 0.5 for this value of k. Determine the peak overshoot and time. This is time. Okay, this is time. Determine the peak overshoot and the time at peak overshoot for a unit step input. Then this is the block diagram. Okay, for a unit, for a characterized open loop transfer function, and here they have given it is a unit feedback. Here it is a unit feedback system. Okay, and the step input, it is a unit step input, unit feedback system and unit step function. So unit feedback, this is g of s, it is an open loop gain. Then this will be the transfer function. Substitute for g of s, you get this expression. The transfer function is going to be this one. Now comparing it with this expression here also I forgotten to write s here. There should be a s term. Okay, compare now. Compare this. Omega n square is equal to k. Then omega n is root of k. Then 2 omega n here, this expression, this is equal to 10. These values are equal to 10. 2 zeta omega n is equal to 10. So zeta is 10 by 2 root k. Then zeta is 10 by 2 root k. But what is the question they have said? The damping ratio of 0.5. The damping ratio should be equal to 0.5. So now substitute. Zeta is equal to 0.5 here. So when you take 0.5, what will be the value? This expression, this should be equal to, see this expression, this value should be equal to 0.5. So in that case, what is k then? K will be equal to 10 divided by 5 divided by 0.5. Then root k is 10. K will be equal to 100. When k is 100, then omega n is equal to 10. So we have found these values, zeta and omega n. Then we have to find the percentage, peak overshoot, percentage of peak overshoot. Percentage of peak overshoot is nothing but a percentage MP is equal to e power minus zeta pi divided by root of 1 minus zeta square into 100. So substitute the values, you will get 16.3. And peak time, pi divided by omega d. Omega d is the this one, it is the oscillation frequency with damping ratio. Omega n is natural value without damping and omega d is with damping. So this value pi divided by omega n into root of 1 minus eta square, and you substitute, you get it as 0.3626. Peak, you get a peak, it will increase by 16% at 0.36 seconds. Third problem, again uh, here we have to find the open loop transfer function for a unit feedback system, which is given by G of S, where I would just ask you to try. I'll just tell you, just try to solve this. We will continue in the next class. You write down this and see if you can solve. We will continue it in the next class. And please see that whatever has been asked in the previous class, yesterday's class, I had given you 3 problems which you are supposed to submit, and it is very clear and we are very serious about it. I have only received for today only one student's assignment, and we are very serious about it. You will have to write it in a book and submit to us. If not, we are not going to evaluate.